Iron is extracted at high temperatures from the ore hematite, which contains iron 3 oxide. Process can be summarized by the equation. So we've got hematite plus 3CO goes to 2 iron solid plus 3CO2 gas. Thermodynamic data shown in the following table. Calculate standard enthalpy change. So that's just calculating delta H of the carbon monoxide, delta H of formation of carbon monoxide. So we use our standard little process, because once we've got heats of formation, or once we've got entropies, we can just say that the delta of the reaction, whether it be H or whether it be S, is where we sum up what we have at the end minus what we had at the start. So in this case here, delta H is what we're interested in. As far as the products are concerned, we got 2 ions. Well, because iron is an element in its standard state, its heat of formation is 0. So thus we have 3 CO2s. And then in terms of reactants, we have 1 Fe2O3 and 3 COs. Pop in the numbers from the table. So we're told delta H overall is minus 23, and then there's the 3 times the CO2 minus. Notice I'm not clearing this minus yet. I want to do this step by step so I don't lose some negatives. We know the Fe2O3 is minus 826, and there's 3x. So playing around with everything, 3x turns out to be minus 333, so x is minus 111 kilojoules per mole. So continuing on and putting in what we found about the heat of formation of CO into the table, minus 111, explain why the standard entropies of carbon dioxide and carbon monoxide are significantly greater than those of iron 3 oxide and iron. So there's the entropies in blue of CO and CO2. You can see they're nice and big because they're gases. And gases have hardly any forces holding them together, so their motion positions are random. In other words, high entropy. On the other hand, if we look at the ones in green, iron 3 oxide and iron, those are solids. Solids, of course, held in a nice lattice, a regular pattern with nice strong interparticle forces, much less freedom of motion, less disorder, thus low entropy. Continuing on, same reaction. The standard entropy change for this reaction, delta S, is plus 9. Calculate delta G. Well, we were told delta H right from the start. We're now told delta S. So therefore we take delta G is delta H minus T delta S. Pop in the values. Delta H we're told minus 23 kilojoules per mole. Temperature 298, and we're told delta S 9 joules per Kelvin per mole. Very important at this point, you notice that delta H is in kilojoules, delta S is in joules. You cannot combine apples and oranges, kilojoules and joules, so we have to convert. I usually convert delta S. So instead of it being 9 joules, it's 0.009 kilojoules. Now we can multiply it out and determine delta G, minus 25.7 kilojoules per mole. And explain why this reaction is feasible, spontaneous, at all temperatures. Well, if we think about it, delta G is going to be a negative number, that's the delta H, minus a positive, that's for the temperature, times a positive, that's for the delta S. Okay, and when you've got a negative number minus a positive number, the new number is going to be even more negative. So it doesn't matter what the value is of temperature, because it's a negative number minus a positive number, delta G is always going to be negative. And if delta G is always negative, the reaction is always spontaneous, otherwise known as feasible. Many industrial processes use high temperatures even when the reaction is feasible at low temperatures. Why high temperatures are used? Because of course you've got thermodynamic considerations that we're talking about here. You also have kinetic considerations, and high temperatures will speed up the reaction. Regardless of the thermodynamics, high temperatures will speed up 99.99999% of reactions. Okay, endothermic solid-solid reaction during chemistry, some do occur spontaneously. One such example, reaction between barium hydroxide and ammonium chloride. There we are. Reaction could be represented as follows. Why is there an increase in entropy for the reaction? Well, any time that you have no gases. In this case, we've got lots of solids, and then we are making 2 moles of a gas. You know there's going to be an increase in entropy. Okay, that should be pretty much a standard answer in your lexicon. The entropy values, the compounds involved given below, calculate the entropy change. Well, again, we know the entropies of all the different species, so we just say that the change in entropy is the entropy at the end minus the entropy at the start. We have, and this is just one of those nice long ones that goes on and on and on because we got lots and lots of species involved in the reaction. We've got 2 ammonias, so we want the entropy of ammonia. We've got 8 waters, so the entropy of water. We got this barium chloride with 2 waters stuck to it, so we need that, and that's all the products. And then the reactants, we got the barium hydroxide and 2 ammonium chloride, so we have to have 2 of those. Take all the nice values that we're given, pop them in, calculate it out, and you get delta S 530 joules per Kelvin. Again, let's make sure that makes sense. Well, of course, part 1, we weren't expecting an increase in entropy, so we're expecting a nice positive number here. And if you want to take a bit further, you're going from solids, not just to 2 gases, but to a ton of liquids as well. So you'd expect it to be a relatively large increase in entropy. Calculate the free energy change for the reaction. Well, we're now given delta H, and of course we just calculated delta S was 530 joules per Kelvin. So therefore, pop in all the values. Delta G, 135 kilojoules per mole minus 298 Kelvin, 25 Celsius, 530 joules per Kelvin per mole. Well, again, cannot mix kilojoules and joules. So let's turn the joules into kilojoules. 530 joules becomes 0.53 kilojoules. Punch it in. Delta G minus 22.9 kilojoules per mole. This is a negative value of delta G, thus the reaction is spontaneous, which of course you A-level people would want to call feasible. Aqua regia, an acidic liquid, it's a lovely one, can dissolve unreactive metals such as gold, can be formed by bubbling hydrogen chloride gas, that's hydrogen chloride gas, through concentrated nitric acid. And I tell you that delta H is minus 69 kilojoules per mole. Calculate the free energy change. Well, we're given stuff about heats of formation that we don't really need as yet because we know delta H overall for the reaction. We're given information about the entropy. From this, we can do, as we have done several times before, determine delta S. So delta S is just taking the S's of the products, so that's NaCl, Cl2, 2 waters. Subtract from that the sum of the entropies of the reactants. There's an HNO3, there's 3 HCl's. Pop in the numbers, punch in the calculator. Delta S is minus 90. Now before I go on, does this make sense? We've got 3 gas molecules to 2 gas molecules, so I would expect a negative change in entropy, so I'm quite happy to see that minus 90. Now we know delta S, we know delta H. We'll pop in for delta G. Again, delta H kilojoules per mole, delta G joules. So let's change that up. So now we've got minus 90 joules becomes minus 0.09 kilojoules. Punch it in, and that's delta G minus 42.18 kilojoules per mole. Squeezing part 2 in here. An alternative method of preparing aqua regia is to use conc hydrochloric acid with concentrated nitric acid. State giving a reason the effect of this on the value of delta G. Well, now what we're saying then is that the HCl is no longer going to be gaseous, it's going to be aqueous. So we have no gases on the left-hand side, 2 gases on the right-hand side, so therefore delta S will be much less negative. Indeed, I would say delta S will probably be positive. And if delta S is less negative or more positive, delta G will be more negative, because as the delta S becomes better, so does delta G become better. Delta S becoming better means becoming less negative or more positive. Delta G becoming better will be more negative. So hydrogen peroxide decomposes slowly at 300 Kelvin, form water and oxygen gas. Reaction profile shown below. Standard enthalpy of formation is minus 286. Use this information on the graph to determine the standard enthalpy formation of hydrogen peroxide. Well, the most important thing here, right, is that delta H, seeing as how we're talking about heats of formation, delta H is heats of formation of product minus heats of formation of the reactant. And we are told that delta H is minus 98 kilojoules, because here's the start, here's the end. Obviously, you lose this energy, which we're going to say is enthalpy, so that's H, and we lose 98 kilojoules for it. So delta H, which is minus 98, is 2 times the heat of formation of water, minus 2 times the heat of formation of H2O. And of course, we don't care about the oxygen because it is an element in its standard state. So we know delta H, minus 98. We know the heat of formation of water, minus 286. So all that's left unknown is the heat of formation of H2O, 2, which is what we've got here. So punch it all into calculators. Heat of formation of H2O2 minus 237 kilojoules per mole. So we use the information given, the heat of formation of water right there. We use the graph to give us the delta H overall of the reaction. Would we expect the entropy change for the decomposition of hydrogen peroxide to be positive or negative? Give a reason for your answer. Well, what do we have here? We've got 2 moles of a liquid going to 2 moles of a liquid, so not a whole heck of a lot of change there, but then making a gas. And if you make a gas on the product side, you can expect an increase in entropy, thus delta S will be positive.